weather, agricultural. In the next hour, we'll learn about extreme weather, agricultural conservation practices, and flood mitigation. Our first speaker is Dr. Steve Vavris. He is Wisconsin State Climatologist and Director of the Wisconsin State Climatology Office at the University of Wisconsin-Madison. Without further ado, take it away, Steve.
All right, thank you, Kelsey, for that introduction. I'm going to share my screen and we can get going. All right, so water quality and flooding are the topics for today, and this will be a tag team presentation between myself and Sherry. I'm with the Wisconsin State Climatology Office and also one of the co-directors of WICI. And the two parts today, Wisconsin's changing climate that I'll cover, and then the more practical aspects that Sherry will address. What can we do about it? To set the stage, I'm going to be using this term frequently, warmer and wetter, because that is a good description for our recent climate change in Wisconsin over the past decades to century, and it's also a good descriptor of where we're expecting to head in the future. To illustrate this, I'm showing the statewide annual temperature in Wisconsin averaged by decade. We've got good statewide records going back to the 1890s. And I'm showing here every full decade through the 20 teens for the annual temperature statewide. You can see that there's fluctuations over time. This one stands out to me. This is the 1930s, the Dust Bowl, a very hot, dry decade. But even by the 1990s, we were creeping above that for our average annual temperatures in Wisconsin. And you see here that the last two full decades have been our warmest on record pretty clearly. Now, just out of curiosity, we're now halfway through the 2020s as of the end of last year. So I was curious, where do we stand halfway through our next full decade? And I was kind of taken aback when I plotted this. This is where we are right now. We are literally off the chart in terms of our annual decadal temperatures halfway through the 2020s. Last year was our warmest year on record in Wisconsin, as well as nationally and globally. So it may not be a complete surprise, but just the magnitude of this change on top of our two warmest decades already really gives us pause. And this is the statewide average for the whole year, but we can break it down now, both temporally and spatially, if we don't go back quite so far to the 1890s, but start, say, the middle of the 20th century, around 1950. And what I'm showing here are the maps of trends by county in Wisconsin for winter, spring, summer, and fall. And this is a 75-year period, so it's a good chunk of time. And it's color coded so that it's fairly intuitive. The warmer colors indicate greater amounts of warming. And so you can see there's various things that you can pick up here. One, if you look at any season for any county, you'll see that there's been a warming trend. And that warming trend has been especially pronounced during the winter. The brighter, redder, orange colors are clearly on the winter map compared to the other seasons. And that's been especially true in the central and northern, and especially the northwestern parts of Wisconsin, where we see anywhere from 5, 6, even 7-degree Fahrenheit warming over those 7.5 decades. Also note the asterisks indicate that the warming trend has been statistically significant, meaning it's not likely to be due to chance and really represents a true climate trend. That's universally true across the state in winter. In spring and fall, these two seasons look remarkably alike, don't they? You see the yellow indicates a 3-degree warming, orange 4-degree warming, very, very similar patterns in the spring and fall, so a moderate amount of warming in those seasons. Summer is interesting in that it has shown warming, but it's not as striking. We see some counties with only about a 1-degree Fahrenheit warming over that amount of time, much more modest, and a maximum of 3 degrees in the state. But even so, you can't find a county that hasn't had some amount of warming in every season. So that's been the dominant climate trend over this period, and clearly winter has been warming the most. The other part of this, though, is the wetter. And so now I can do the same exercise looking at statewide average precipitation instead of temperature. Again, going back to the 1890s, that's the graph on the right. And just like the temperature graph, we see variability by decade. The 1890s were a dry decade, the 1930s Dust Bowl famously so. But even starting in the 1970s, we were starting to see these wetter decades compared to the past. 1990s especially, but boy, the 20 teens just kind of blow you away. That was easily the wettest decade on record in Wisconsin by a good 10%. 2019, the last year of that decade, was the wettest year in Wisconsin's history. And playing that same exercise for where we are right now in the 2020s, halfway through our decade, we're not nearly as impressive in terms of total precipitation as we were last full decade, but we're still pretty high. You notice where this green asterisk is, we would be the third wettest decade on record if the decade ended right now. So this is something to keep in mind. More confidently, will be a very warm decade, but so far we're getting off to a wet decade again in the 2020s. Same format as before for temperature, but now breaking down the county trends in precipitation going back to 1950. Intuitive with precipitation, green means wetter, brown means drier. Winter stands out again, just like it did with temperature. Winter has seen the biggest relative increase in precipitation around the state. These dark green colors represent a 20% increase in precipitation since 1950. In winter, that can be more rainfall, it could be more freezing rain, it could be snowfall, it could be anything that falls in the winter. But some combination of that has been getting much more common. And most of these counties in Wisconsin have seen statistically significant increases in winter precipitation. Now, if we turn to spring, the changes are pretty strong in the southern half of the state. You see these green, dark green colors representing a 20% increase in springtime precipitation. But now it depends where you are. The farther north you go, the more modest the trend toward a wetter conditions in the spring. Fall is more uniform across the state. It's hard to pick a north-south divide. It's more scattered, but most counties, all but about one, are showing some increase in fall precipitation. But summer, once more, is the oddball, just like it was for temperature. Here, it completely depends where you are in the state. If you're in the central and eastern parts of Wisconsin, you've seen a 20% increase in summer rainfall. That's really substantial. But the farther north you go, the drier the trend has been. And in fact, the trend reverses sign, and we actually see drying over this 75-year period, especially as you go into the far northern counties, one even significantly so. Summer rainfall tends to be spottier, so it's not a complete surprise, but it is noteworthy that summer is the season where there's differences even in the sign of the trend, depending on where you are. One thing that's been consistent, though, is that regardless of the season, we're seeing more heavy events when we do get precipitation. And that was never more true than during the 20 teens, that very, very wet decade in our state's history. We can look not just at those trends in total precipitation that I just showed, but the extreme daily amounts that we received. Showing here a map of so-called 100-year daily rainfalls. These are rainfalls that are so heavy, we expect them to happen only once per century on average. But in fact, we had 21 such events during the 20 teens decade. And you can see from the dots where they occurred. You can see the amounts that fell next to them. Some of these are staggering, like the nearly a foot that occurred in Western Dane County in August of 2018. That takes the cake. But all over the state, north, south, east, and west, we see examples of this, of these really heavy deluges. And predictably, when these happen, the infrastructure is not able to handle them. And we end up getting these very expensive and dangerous flood events. I'm showing a few here. One famous example, it hit Saxon Harbor in Iron County in July of 2016. Up to 10 inches of rain fell in multiple days, causing more than $40 million in damage. Another one, if you were around about 20 years ago, the Lake Delton floods in 2008 just were staggering. Here's Highway A being completely ripped apart as the waters burst through. We saw videos of houses falling into the lake. It was just disasters galore around Lake Delton in June of '08. And then the one I mentioned earlier, the 1 day flood in August of 2018 in Dane County. The map on the left shows the estimated radar amounts of how much fell. So the middle blue color is 9 inches to a foot, and the dark blue is more than a foot. And you can see plenty of areas of 9 to 12 inches and a few scattered areas unofficially that picked up more than a foot. It's just kind of mind-boggling. These are more like hurricane amounts, and yet they hit southern Wisconsin. And you can also see that this is mainly where the rain fell. Had it gone just a few miles to the east, it would have been a direct hit on a big urban area of Madison, and the damages would have been even worse than they were. But as they were, we had over $150 million in damage and one fatality of a man being swept away in the floodwaters. So really, really big deal. And we are not alone. Wisconsin has had a lot of these extreme rainfalls, but so have other parts of the country, especially the eastern half. What I'm showing here are the trends in the rainfall amounts on the wettest 1% of all days, starting the 1950s and going to the early 2020s. So what that means is if you take all the wet days during a year with some precipitation and then just lopped off the weakest 99%, you're left with the real big torrents. And the question is, how have those amounts on the very wettest days changed and trended over time? And we can see here that no matter what sector of the continental US you're in, there's been an increase, but especially so here in the upper Midwest, nearly a 50% increase, and in the Northeast, even more so, a 60% trend. And so this is, we're not alone here, and other parts of the country are dealing with these extreme rainfalls as well. Okay, so that's what's happened. Now, what does the future hold? We can't change the past, but we can learn from it, but we can do something about preparing for the future. One thing that we can anticipate is that we're going to likely be seeing more of the same trends that we've experienced to date. I'm showing here an example from the National Climate Assessment from a couple years ago. This is not changes in precipitation, but rather changes in runoff by season or annually. Ultimately, for flooding, it's the runoff that matters the most, not just the precipitation. On the left, we see the annual expected changes in runoff for two scenarios. One is a large climate change signal in the future, and the bottom is an even larger one. So this is, the top one is not great, but the bottom one is even worse. And what you see is a lot of green indicating more runoff all across the Midwest, upper Midwest, in either scenario. So that's something we should plan for. But then on the right, we can break it down by seasons and see the vast differences: winter, spring, summer, and fall. And what really catches your eye once more is winter. Winter is expected to see a pronounced increase in runoff, especially as you go farther north in the Midwest, including all of Wisconsin. Spring is secondarily, especially here in this projection in the southeast, an increase in runoff, maybe less so in the north. Fall, an increase almost everywhere in the state, but not as pronounced as during winter. And then summer, it's a mixed bag. Some places showing a decrease in runoff, some places a slight increase. That reflects the fact that climate models don't agree on the sign of the trend in summer rainfall, something that requires more research. But winter and spring really stand out as the bigger seasons for runoff changes. And just to emphasize this point about why that matters, there's various factors that confound problems when we have winter and spring runoff around here. One is that it often coincides with snowmelt, especially if we get rain on snow. We also have frozen ground in the winter, and we saw great depths of frozen ground this winter without much snowpack. That's likely to continue in the future, even in a warmer climate. There's manure on fields and there's runoff. The water quality problems become that much greater. And then wet soils become an issue, especially in the spring during planting season. So we know all of these things, but it's a good reminder of why these projected increases in winter-spring runoff are so important for water quality. Now, why do we expect these trends in extreme rainfall to happen? Well, it comes down to the water cycle. This is a graphic that's sort of taken out of a high school geography or Earth system class, but it bears repeating because the key elements of the water cycle and the climate system involve evaporation from the surface, whether it's soils or crops or lakes, streams, whatever, and get evaporation into the atmosphere, condensation in clouds, that precipitation falls out, and then it has to go somewhere. So it runs off, eventually reaching groundwater, reaching surface waters, and so on. So that's the water cycle naturally. And when we get a warmer climate, the water cycle simply strengthens. So all of these elements become greater. We get stronger evaporation from the surface. We get heavier precipitation events. And then consequently, we get more intense runoff. So all of these things are just sped up in a warming climate. And we can even uh, quantify this process because we know physically that a warmer atmosphere can simply hold more moisture, which means there can be more intense precipitation when the weather conditions are right, like when we have a stalled weather front. And we know that a 1 degree Celsius or 1.8 degree Fahrenheit increase in the air temperature means that the atmosphere can hold 7% more water vapor. And this is especially a big deal during the summer when we have a muggy day, lots of humidity. If we have 7% more water vapor possible on top of what's already a large amount of water vapor in the air, that can lead to a rich reservoir of moisture that can be tapped for these heavy precipitation events. Now, where do we expect extreme precipitation to go in the future? Well, as you've gathered from what I've said, more of it. Here's a projection that we've put together from the Wiki project. Expected days with 2 inches or more of rainfall. This is for mid-century, around 30 years from now. On the left is the frequency of 2-inch or heavier rainfalls in Wisconsin during a recent climate period from the 80s through 2010. The blue colors represent where we get more of these heavy rainfalls typically. The bar here, the color coding is days per decade. Just for reference, around Madison, we typically get about 1 of these per decade, per year rather, so about 10 per decade. They're most common in the south and western parts of the state in the past. And in the future, the projection is for the years ahead is that that pattern will more or less continue. There'll be more common flooding events or heavy rainfalls in the south and the west, but everything goes up. Pick your county, pick your location, and we're expecting to see more of these heavy rainfalls. And if you have time to study these maps, sometimes you can pick your county and see how much the projections are indicating a rise. We also have confidence that for the seasonal precipitation patterns, that winter and spring will again be the ones that show the biggest increase, just like they have already. In the upper left here, this is the projected change by mid-century in total seasonal rainfall, or precipitation rather, in winter compared to the recent past. So anywhere from about a 10 to 15% increase on top of where we already are. Spring, uniform increase across the state, mostly about a 10% increase. Similar in autumn, but only about a 5% increase. And then summer, a mixed bag, because as I said, climate models are not agreeing up to now on whether we'll see more summer rainfall or less. And then I just want to make a final plug here before I wrap up for the WISCONet, the Wisconsin Environmental Mesonet. This is a new statewide network of weather and soil monitoring stations, if you're not already familiar with it. There's going to be at least 1 station in every Wisconsin county, up to a total of 90. 58 have been deployed to date, and by the end of this season, or at least the end of this year, WISCONet hopes to have 1 in all 72 counties. It's great because it provides real time, every 5 minutes, weather and soil temperature and moisture data. And the weather variables are shown here, the basics plus things like solar energy and leaf wetness, and of course the soil conditions at 5 different depths down to a meter. Major takeaway points from my section for today's talk. Warmer and wetter, as I keep saying, that's been the trend in the state up to now, and it's projected for the future. Winter has been the season warming the most in Wisconsin and summer the least. We've seen the largest relative increase in precipitation during winter, and that's been the case so far, and it's expected for the future. And then I've emphasized winter and spring showing the clearest signs of a wetter future, whereas summer's change is less certain. We're confident that with a warmer atmosphere, we'll be seeing more extreme precipitation, as we've already been seeing. And then finally, winter and spring runoff concerns will likely amplify. And that's going to be for various reasons. More of the precipitation is likely to become rainfall in the future, more rain on snow events, and probably more intra-seasonal snowmelt events during the winter rather than building up in the winter and having a big springtime pulse, as was more the case in the past. So I will stop with my portion and hand it over to Sherry. If we do questions at the end, we can take turns with any questions that you have. So I will stop sharing here and hand over the baton.
Thanks so much, Steve. That was a great presentation. Before we transition to Sherry, we're just going to launch a quick poll to collect some demographic information from you. This anonymous information helps us evaluate the audiences we are reaching with this type of work. So please fill it out. It really helps us with our work. And then just a heads up too, at the end of this webinar, we'll have another topic, another survey question where you can self-rate your experience with this program. And this really helps us improve our future programs as well. So I'll just give you a moment to answer that. And yep, feel free to put questions in the Q&A chat as well. And we will kind of do those at the end of Sherry's presentation. So just give another minute here for the poll. Before we transition out of that, I will introduce our next speaker, Sherry Schwartz. So Sherry is an agriculture water quality outreach specialist with UW-Madison's Division of Extension, based in La Crosse, Wisconsin. So whenever you're ready, Sherry, you can take it away.
Great. You can see my slide, Kelsey?
Yep, it's on the Why Does This Matter slide.
Excellent. Excellent. Okay, thank you so much for that introduction. And Steve really set me up well. I think we work together well here. So you heard from Steve about what is the weather doing here in Wisconsin? What are we expecting the weather to do in the future? And I'm here to relate that to agriculture, conservation, and water quality, and also talk a little bit about flood mitigation and what ag water quality has to do with that. So Steve shared a few examples of extreme weather in Wisconsin in the past few years, but for me, I wanted to sort of share a story about how this matters to me as the ag water quality outreach specialist for Western and Southwestern Wisconsin. So in 2018, there was that rainfall in southern Wisconsin, and that also included a storm in August of 2018 in the Coon Creek and West Fork Kickapoo watersheds, which are just south of La Crosse here, where I work. As you can see in this picture, this was quite the deluge. There was a significant amount of damage, $3 million in damage to homes and businesses in the town of Coon Valley and across Vernon County, where Coon Valley is, $14 million in damage to public infrastructure. And part of that infrastructure included the catastrophic failure of 5 dams in the West Fork and Coon Creek watersheds. You can learn about, by the way, residents of Coon Valley and the area's personal stories through a link in the chat. So what does it look like when these earthen dams break? Well, here is what we can see from the Coon Creek watershed here. You can see the remnants of this earthen embankment to the left, and then where it attached to the valley wall and where that extreme storm in August of 2018 just created too much water for this earthen dam to withstand. And as a result, a huge amount of water then went through the Coon Creek and West Fork Kickapoo rivers. Because of these 5 catastrophic failures, all of the dams, all 22 except one, are being removed as soon as possible. And farmers and local conservation departments are asking, what can we do? What can we do on the landscape to help mitigate floods, to help keep water on our fields, and to, attempt to counter for the removal of these immense structures which are meant to prevent floods. There is a producer-led watershed group in the Coon Creek Community Watershed Council, and in the chat you can read an article about their stance on these dams being removed and what their plans for the future are. So as Steve showed you these same maps, but with 2 inches of rain, and I'm going to show you the ones with more than 4 inches of rain. So you can see Coon Valley called out here, both Coon Valley being in southwestern Wisconsin. And as Steve said, in southern Wisconsin, even historically from the period of 1980 to 2010, we see that in southern Wisconsin, there were already more days per 100 years when there was a chance of getting more than 4 inches of rain in 24 hours. As we look to the future, mid-century, 2040 to 2060, in a mid-level scenario, we can see that in southern Wisconsin in particular, but northwestern Wisconsin as well, the number of days per 100 years where it's could be possible to get more than 4 inches of rain goes from single digits into the double digits, and as high as 16 or 18 days per year. And that's just talking about 4 inches of rain or more. And that can include in August of 2018, when nearby Coon Valley, a rain gauge measured nearly 10 inches in one day, which is way more than 4 inches. So we're talking about really extreme events, as Steve already very clearly pointed out. The good news is that there's many different ways to slow down water on the landscape. These are often categorized as natural infrastructure when you're talking about them in terms of flood mitigation. But these solutions can reduce runoff year-round, not just during the summer storms that have caused these flooding incidents. And as Steve pointed out, this is important for especially winter and spring, when we can see really high amounts of runoff and when we get a lot of our precipitation more generally. These whole landscape solutions can require many acres, especially when we're talking about infield practices such as cover crops. But that means we don't need to take land out of agricultural production. We just need to implement accepted conservation practices that can reduce runoff and which we know can also improve water quality. These include practices like reduced tillage, keeping living cover on the landscape or cover crops, or relay intercropping, as well as edge of field or structural practices such as at-grade stabilization structures, also known as check dams, perennial or native buffers and filter strips, restored or constructed wetlands, all the way on down to two-stage ditches or stream bank restoration. So a great way to approach this can be layering these practices on the landscape. Everybody loves cake, and cake has layers, and so can these edge of field and infield practices on a farm, such as this aerial photograph shows. This farm has grassed waterways, filter strips, a restored wetland, a riparian forest buffer, and others. And there is still lots of agricultural production happening on this farm, but there's also area dedicated to improving water quality and reducing runoff as well, addressing that water quantity question. Extreme precipitation, like 10 inches in 24 hours, can overwhelm any one infield or edge of field practice. But each of these practices can contribute a small amount, and layered and combined together, they can increase a field or an entire farm or an entire community's capacity to deal with the deluge. So jumping into the first practice I want to talk about, no-till farming can improve infiltration over the long term by improving soil structure and water holding capacity. This data from Wisconsin Discovery Farms shows that the runoff in soils classified as with high infiltration rates or moderate infiltration rates can have reduced total runoff during the non-frozen period. I think it is important to keep in mind that this graph does show not very many no tillage sites, and these are all from one particular area of Wisconsin with one particular, one particular farm. But you can see that it has the potential to reduce those extremely high runoff events. The median of both of these box plots is around the same, but the overall range of the no tillage category is smaller. This is a little bit more nuanced because there are exceptions. In some soils, such as slow or very slow soils with very slow infiltration rates, no tillage can actually increase runoff because of soil consolidation and the smooth, even surface, allowing runoff to move more quickly. But there was a UW-Madison study from 2023 that showed that crop residue greater than 30% of surface cover can reduce runoff, both in no tillage and in tillage systems as well. So it's with careful consideration to use no tillage as a runoff reduction practice. We know that it has water quality benefits and can reduce soil loss and nutrient loss. When it comes to runoff, it can be nuanced, so you want to look carefully at the soil type and other practices. If you can function with a high residue system, then maybe this is something that could help reduce runoff on your farm, but it's not going to work for everyone. So with tillage, the defining factor was how much crop residue is on the soil, protecting the soil from precipitation and runoff. And that applies to systems that keep living cover on the ground all year as well. By protecting the soil with cover crops, we can reduce runoff and other losses as well. Discovery Farms measured lower soil and phosphorus losses from a grain field in southern Wisconsin following the introduction of a rye cover crop. It's important to note that these reductions were only significant during the non-growing or cover crop season. But as we saw from Steve's presentation, that non-growing season, winter and early spring, is a really important time for runoff. Can be a period of increased runoff in Wisconsin. So knowing that protecting the soil with a cover crop can affect that during that important season is a valuable tool. We also have UW-Madison research, showing that a clover cover crop planted after corn silage in southern Wisconsin reduced runoff volume by 50% compared to no cover crop. But once again, the percent of ground cover was the primary factor in reducing that runoff. So when it comes to runoff, just having biomass, having plants on the soil, especially during winter and spring, is what's important. There is also some info from Iowa State University to show that relay intercropping could be a strategy to reduce runoff as well. And all of these have one thing in common: having biomass on the field, having plants on the field all year round. Moving from infield practices to edge of field practices, I think a really foundational one is vegetated buffers or filter strips. These can reduce runoff by increasing storage capacity, evapotranspiration, and infiltration within that strip. These work by slowing water down. So once runoff moves off the field, it can slow that water down, allowing particulate contaminants such as soil, such as particulate phosphorus, to settle down into that strip. Those plants then can uptake those nutrients and as they grow throughout the year, increase soil structure and increase infiltration. And then the whole reason we would be talking about these is that they are another layer to protecting surface water. So if those infield practices, such as a cover crop or no tillage, is overwhelmed by the amount of precipitation and runoff does start to move off the field, then you've got your secondary layer, your vegetated buffer or your filter, there to protect that runoff from moving any further. A native prairie strip can be an alternative, a similar device, a similar practice to a buffer strip or a filter strip, but of course with native prairie plants instead of a non-native plant. There's research from Iowa State to show that you only need to dedicate 10% of the row crop field to prairie in order to have some pretty significant results in all of these factors, including a 37% reduction in runoff and high reductions in soil loss and surface phosphorus as well. The big difference between a native prairie strip versus a perennial grassed buffer or filter strip besides like the type of plants themselves, is that you can harvest for forage a filter strip or a buffer strip, whereas you cannot harvest a native prairie strip for forage, and it requires different kinds of maintenance. Moving from sort of edge of field practices, we're going to move to talking about structural practices now. So the first one I want to talk about is also considered an edge of field practice, but it requires some engineering, and that is grade stabilization structures. These are also known as check dams, and I even know one conservation professional who lovingly calls them grade stabes. So these can go by a number of different names, but essentially they function as a very small dam. They are designed to slow down and retain surface runoff for a time by essentially creating a pond and then allowing the water from that pond to move out very slowly through an outlet pipe. We have Discovery Farms data to show that these can slow water down and can have their data showed reductions in soil delivered to a nearby stream on a Western Wisconsin farm. So these can have water quality benefits as well as slowing that runoff down for flood mitigation. The next structural practice I want to touch on is restored or constructed wetlands, which are an accepted practice by the NRCS. As we move through this picture here, so you have a nutrient inflow load coming from surface runoff that can move into this restored or constructed wetland, and then they actually function somewhat similarly to the grade stabilization structure. They basically provide a place for that water to slow down or stop entirely, allowing contaminants to settle to the bottom of that wetland or to that pond. And this can retain phosphorus and nitrogen. As you can see in the bottom right corner of this picture here, there are some numbers on those nutrient reductions or retentions. And then there is also an outflow. So once that water has slowed down, it is allowed to go back out of the wetland, but now with less nutrients, less soil in it, and at a much slower pace. My final example of a practice that I want to touch on is these are structures that are currently being inputted in Outagamie County and studied by USGS and UW Green Bay. An agriculture runoff treatment system actually takes its cue from wastewater treatment systems. So if we want to move through this practice, you talk about layering. This is sort of a cake within a cake, if you will. It's got layers, and you can layer it with other practices if you wanted. So if we start at the top, we can see that this is a 20-acre watershed being converged together and then run through a short section of subsurface drain tile. And then moves into this pink area, which is called a sediment forebay. And that's the first time that the water is going to slow down and sediment is going to start to settle out. It's going to then move through two sets of a gravel spreader bar and a treatment wetland cell. That's going to slow this water down even further, allowing even the smallest sediment particles and the particulate phosphorus attached to settle out, slowing down, allowing nitrogen to settle out here. And if these have wetland plants in them, then those wetland plants are going to take up those nutrients and keep them from moving back out of the system. There is a final sediment trap, and then this particular one also contains a water control structure and a phosphorus removal system before finally being discharged to an existing natural wetland as water that has 80% less suspended solids than when it came in and 60% less particulate phosphorus. These systems essentially combine accepted conservation practices such as sedimentation basins, constructed wetlands, water control structures, and grade stabilization structures. And they are a classic example of this layering, and they are currently being studied here in Wisconsin, which is really exciting. So when we talk about putting these practices on the landscape, I think it's really easy to maybe think about them as a pyramid. You start with a foundational accepted conservation practice such as no-till, and then you move towards like a final goal on a particular field or on a particular farm. When it comes to extreme weather, one way I like to think about it and like to explain it in is maybe thinking of it more as a sideways pyramid or a play button. So, yep, you're still going to start at the beginning. You're maybe going to start with no tillage for soil loss. But as you need to widen that field's ability to deal with extreme weather, then you're going to maybe add your next practice. You're going to press play to the next track on the album. You're going to add high residue, maybe to reduce runoff. And then if you need to widen your ability, you need to widen your stance even further to deal with that, with our extreme weather here in Wisconsin, maybe you add a cover crop for nutrient loss as well. So each step of this has widened this field stance and the capacity for this farm in this field to handle the overwhelming precipitation. What does this actually look like on a field, on a Wisconsin farm field? So on this particular farm, we've got lots of layered practices going on here. We've got a wetland, we've got a vegetated riparian buffer, we've got a prairie strip, a classic edge of field practice, we've got an at-grade stabilization structure, and we've even got infield practices going on like cover crops. Each of these is going to provide a little bit of benefit, but layered together, when you're faced with overwhelming precipitation, each of these is going to be able to contribute some to widen this farm's ability to deal with extreme precipitation. So I really want you to leave my section of the presentation feeling empowered. Where there's a will, there's a way, right? We know that reducing runoff from ag fields can be done by accepted conservation practices, ones that we are familiar with. These each have smaller effects than huge dams like the ones being taken out in the Coon Creek and West Fork Kickapoo watersheds. But by layering practices on farms and in an invested community, the impact could be substantial. These practices do also have the added benefit of having a positive impact on surface water quality, which is a benefit to us all. Thanks so much. That's the end of my presentation.
Thanks so much, Sherry. So we so far have one question that came into the chat, but I'm just going to read it aloud too, because some other folks in the audience might kind of find it interesting as well. So is there any Wisconsin data that shows historical groundwater elevations and or forecast for groundwater elevations? It is very likely that wetlands in my area are getting larger and wetter. I have a hard time finding great historical data for groundwater elevations that we can use kind of in a public space or with the public. Do you have any information on that?
I don't know if you do, Sherry. I do know that it can get complicated in some areas because of groundwater pumping, but if it's more of a natural area, I would be interested in that too. I mean, the groundwater levels are measuring more of the long-term variations over a year or years. So we had a lot of high groundwater levels at the end of the 20-teens because of that wet decade and the last year or two being especially wet. But I don't know the answer for that. I can try to find out. I'm curious as well.
Yeah, I'm sorry. I don't have a great information to add either. I don't believe there's any information on groundwater in the most recent wiki report, but potentially in some of the working group reports, you might find that there's some information in there. So digging even deeper into that wiki information, you might find what you're looking for.
Great, thanks so much. So feel free to type in any questions you have in the Q&A box. In the meantime, I will get the CCA credit kind of pulled up. So if anyone now needs to scan that for their continuing education credits. Hopefully everyone's able to see that, and feel free to put your number in the chat too as well if you're unable to scan today. Okay, so we had another question come into the chat. Is there any best guesses on how much in ARTS, so that's the agricultural runoff treatment system, costs for that 20-acre example?
That is a really excellent question. I do not have the numbers, but I believe I had a link available to go to the Outagamie County Land Conservation Department, where they highlight the different projects that they have been working on. And you might find that in one of the reports there, they have information on how much that system costs, or through the Fox Wolf Watershed Alliance, which is in cooperation with the Outagamie County Land Conservation. So I don't, but it might be somewhere in there.
Great. And it looks like we have another question that came in. Do you have any outlook for severe storms, tornadoes, and flooding in the next 1 to 5 years versus the previous history in Wisconsin?
Good question. Yeah, especially as we ramp up into severe weather season here in March and April. When it comes to climate change and severe storms, it gets real tricky. For one thing, climate models are not fine scale enough to simulate tornadoes. And so we don't have a direct sense of even which direction tornadoes are going to go, more common or less common in the future. When it comes to severe storms, those are especially important because those are the events that cause the most expensive damages around the state and around the country, but particularly in Wisconsin, from damaged fields, damaged roofs, and structures being knocked down, and so forth. With severe storms, we do have a tug of war expected in the future. That is that what you need for severe storms is warm, humid air near the ground, and that rises and provides fuel for these severe thunderstorms. That should become more common in a warmer future. So in that sense, we would expect more extreme storms. But at the same time, you also need wind shear, meaning that you have an increase in wind speed or velocity with height. Strong jet stream winds, for example, are very favorable for producing severe storms. We expect that wind shear to weaken in the future as the jet stream weakens during especially the summer months. And so we've got this competing effect, the warm, humid air near the ground favoring more severe storms, the weakening winds aloft favoring fewer. So it's really difficult right now to know which side is going to win that tug of war, and it may differ over time. Maybe one side wins early on and then the other side wins later. So this is a great question. It's a real popular research topic, and as climate models become better and finer scale, we'll hopefully have a better answer within the decade.
Great, thank you. We had some other questions come in. So one of the first ones is, how much cover crop biomass is needed to protect fields from extreme storms in late winter and early spring? Are winter kill cover crops sufficient for reducing runoff and erosion?
So, I think that there will be some numbers coming soon. I mentioned the 30% of crop residue. That's a little bit different than cover crop biomass, but they are somewhat related. Based on some information from UW-Madison, I believe we'll be able to say that around 1,500 pounds of cover crop biomass per acre can have a significant amount of protection, particularly during that late winter, early spring period. So around 1,500 pounds. And then there's more information out there about like how much you want as a maximum as well before that starts impacting your crop yield. But as far as a minimum, that's one number to keep in mind.
Great, thank you. So we have some more that came in. This one's directed at Sherry. So some of the practices you mentioned will take a lot of resources, whether through cost share or staff time. Since those are both limited, what tools or models can we use to prioritize the most important places to focus for reducing effects of heavy rain and runoff?
Ooh, okay. That's a great point and a great question. As far as like easy tools that I can necessarily send you to right now, I don't necessarily have like a link or a name for a tool. I do know that depending on your county, talking to someone at your land conservation department might be helpful. I've definitely been to meetings where the Vernon County Land Conservation Department has people on staff who are working on models to be able to point out where should they be putting these ground stabilization or these grade stabilization structures to be having the most benefit. I think that there's a point, if we're talking about like wetlands, for example, some of those, depending on the size, are going to be more helpful further up in the watershed, so where the streams are even smaller versus further downstream. So it's going to differ based on the practice, what's going to be the best place to put that. And I don't have like a quick, easy tool or model, but I know that in some counties, that's something that they're working on having in place. So maybe contacting your county LCD as a start.
Great, thanks, Sherry. And we have one more that came into the chat. It's also kind of related to modeling. So another key question with structural practices like that arts you were talking about is how much area they can treat. Most treat 15 to 30 acres. To achieve watershed-wide benefits, how many structural practices will be necessary? So I don't know if you have any comments on that, but kind of similar to that last question as well.
I'm sorry, I'm going to answer more generally here again, which I'm sorry is maybe a little bit vague. But I think that, I mean, if you were looking at just one practice, yeah, you could probably look at like, okay, you just multiply the amount of acres that arts can cover by the size of the watershed. I think what's more important is keeping in focus that layering of different practices. So in arts, is treating the runoff after it's left the field, but also looking at infield practices. And those edge of field practices like buffers and filter strips, even grassed waterways to help with some of these issues. I think that if you're looking at exactly how many acres, that can be really expensive to have that kind of data collected and then spat back out for a particular watershed. Yeah, I don't have like a specific answer of how many you would need to have in place. Quite a few, I think, is what I'm trying to say, is that you need to have community buy-in. That's why it's really neat to see producer-led watersheds like the Coon Creek watershed group wanting to implement these practices on a watershed-wide basis, because you need that buy-in in order for these to really make an impact.
Great, thanks, Sherry. We'll give you a break now and direct this next one for Steve. Steve, do you anticipate that our changing winter conditions will change the magnitude of late winter, early spring surface runoff?
Yeah, so the surface runoff late winter and early spring. I think based on what I showed, I think that that's likely to increase. Um, the one possible exception is, as I alluded to at the end, in sort of the traditional past in Wisconsin, colder winters, big snow buildup, gets thick and thick and thick, and then by sometime in March or April, we get a big spring flush. Um, that produces a very narrow peak in runoff. And I think what we're going to be seeing in the future is more periodic melt events and runoff events during the winter itself. And if that happens, there might not be as big a spring pulse as we used to see. But the concern is that we're going to be seeing more of these intra-winter runoff events while the ground's still frozen. And that could be a real concern. So the precise timing of late winter, early spring changes in that peak, it's a little hard to say. But when you look at that map of changes that I showed earlier, boy, winter looks like a big increase in runoff. And in the spring, most of the state, especially southern and eastern Wisconsin, were in the crosshairs for more spring runoff as well.
Great, thank you, Steve. And our last question, it looks like, though we still have a few minutes, for Sherry. Are you or in Wisconsin seeing an uptick of some of these implementation of these strategies you talked about today? Are any more popular than others? Could you speak on that at all?
I think that based on some information from UW-Madison researchers looking at producer-led watersheds, we are seeing an uptick of implementation of some of these conservation practices that I've mentioned, things like cover crops, things like no-till. These are being encouraged through the producer-led watershed program and in other areas as well. I think it would be difficult to say too much if any of them are more popular than others. Definitely reduced tillage is a really important one, and one that we've seen an increase of, and an increase in the use of cover crops as well, as more inputting cover crops can take some expertise maybe from outside. So as more farmers put them in, then there's more people to ask for advice and people are more comfortable giving them a try.
Great, thanks so much. Well, I want to thank you all for spending some time with us here today and those great questions for Sherry and Steve. We invite you to visit our Agriculture Water Quality Program website for other content. We will also have recordings for all of the webinars on here. It really just takes a couple weeks after the webinar to process those videos. So thank you again so much for joining us for the 2025 Agriculture Water Quality Webinar Series, and we really hope to see you next year. Have a great rest of your day, and if you didn't already answer that survey question, we would super appreciate that to inform future programming. Thank you so much.
Thank you.